All right, so let's test. Can you guys hear me?
Yes.
Thank you. All right, so today what we're going to focus on is looking at the theories that we have discussed with regards to understanding metal ligand interaction within coordination compounds to appreciate spectroscopy. So what we will focus on is electronic spectroscopy. And here, we're actually going to use the simplified theory, crystal field theory, to give us an insight into this electronic spectrum. All right, so in the recent lectures, we looked at molecular orbital theory combined with group theory in order to evaluate the covalency that does exist within metal ligand interactions. And we focus on the interactions between metals and ligands that are primarily sigma donors. And so that's when we establish the sigma-based molecular orbital diagram for an octahedral compound. And then we talked about ligands that have the capability of interacting with metals via a pi interaction. So we focus on ligands that have pi donor capability. We develop the molecular orbital diagram with respect to that type of ligand. And then we focus on ligands that have the pi acceptor capability. And we talked about this idea of metals being a source of electrons under these conditions and how you can have metal back bonding. We also provide a context for this general trend of coordination compounds or these type of metal-based compounds having a total number of electrons within the, what's basically shared by the metals and ligands, and that typically affords greater stability. And we finally looked at how metal ligand back bonding can affect certain acceptor ligands like the carbonyl ligand and focused on the transinfluence in terms of how it impacts the spectroscopy or in that case, the vibrational spectroscopy of that molecule. So what we will focus on today is electronic transitions that can occur within metal ligand complexes. And we're actually going to focus on two main types. There are a number of them that are possible, but for the scope of our course, we'll only really focus on two. And so one of the types of spectroscopy has to do with electronic transitions that can occur within the d orbitals. And so we're going to have an introduction to these type of transitions. And so when we focus on excitations of electrons that are in a lower energy d orbital to a higher energy d orbital, these type of transitions tend to be visible in the actual visible range of light. So this is something that we can perceive. And so here we're going to look at the influence of the spectrochemical series as I've defined previously, going left to right. The trend is that we're looking at how the magnitude of delta is actually increasing. And that has to do with the properties of the ligand, whether it can have pi donor capability, and that's what you see to the left, or whether it has pi acceptor capability, that's what you see to the right in terms of how it fine-tunes the magnitude of delta. All right, so let's focus in on this idea of delta as a measurement of the difference in the energy of the d orbitals, but focusing on those metal ions that have electrons that are going to go into those orbitals. And so here we have an example of a cobalt octahedral complex. And so here we're talking about something very general. We're not actually defining the ligands themselves here, especially since we're going to use crystal field theory, which negates the identity of the ligands and basically treats them as point charges. And so when we're talking about cobalt-3, we're talking about a D6 electron configuration. And so when we put that type of metal ion into an octahedral field, well, we have this very typical splitting into our EG and our T2G orbitals. And so depending on the magnitude of delta, whether it's small, so that being a weak field, or whether it's big and that being a strong field, we can have the high spin range of this, which would be a spin of 2, or for a strong field, the low spin, and that would be your spin of 0. And so now we have to think about, well, how does this impact the possible electronic transition from a lower energy orbital, so the T2G orbital, to an EG orbital, whether we are in a weak field situation or we're in a strong field situation. All right, so that's what we're going to be focused on today. So as I already mentioned, these type of electronic transitions, which we can simplify the terminology as DD electronic transitions, well, we can focus on this from the perspective of that magnitude of delta octahedral. And since this is something that you can visualize in the visible field, well, we're going to look at the color wheel, which is a representation of the complementary nature of what you will observe based on the absorbance. Okay, so a few things that I want to iterate. So delta octahedral, if you go back to the previous slide, okay, right, that is a measure of an energy difference. And so that in our context can be seen as a measure of that difference in energy between the T2G lower energy orbitals and the EG orbitals for an octahedral complex. Well, from that perspective, then we can look at the spectroscopy. And so this, in this context, would be visible spectroscopy. The type of technique you would use would be a UV-vis spectroscopy using a spectrometer that can give you this capability. And so you're just looking at the correlation between delta and the wavelength, lambda. So that's what you normally are going to visualize. And so that relationship between the energy and a reciprocal relationship with the wavelength. So obviously, the higher the delta is, the lower the wavelength is going to be. So when we're focusing on the color wheel, here we're just looking at this idea of if you see something absorbed in a certain region, so let's imagine we're absorbing here in the violet. Well, what you will actually see is something in the actual yellow range. So that's basically the complementary nature of the color wheel. And so here I want to give that reflection of, well, how does that impact the type of compounds we're focusing on, and specifically on the coloration of, where we're going to see the excitations of these type of compounds. So here, again, I'm being specific to cobalt because that is a metal ion that does have d orbital electrons, and also it's a representation of a metal ion that has a weak field and also a strong field, capability. And so a reflection then of the spectrochemical series, right, this arrangement of these ligands, is that we are going to see a difference in terms of the energy of excitation. And so here's just a sort of a cartoon representation of if the ligand for a cobalt 3+ complex is entirely consisting of cyano ligands, well, you see the representative coloration of that compound, where if you were to switch from the cyano ligand to now, let's say the amine ligand, all right, and if you look at the spectrochemical series, well, where are we going? So we started off here, the cyano ligand, and then we moved over to the amine ligand, right? So when ammonia coordinates to the metals in amine, we're going from something that is a pi acceptor to something that is predominantly a sigma donor. Okay, and so here then, what we see is a change in the coloration because we're looking at the change in delta. And then if you go all to then the ligand being the aqua ligand, so replacing all these ligands that are on this coordination complex, we're further going in this direction. So the delta magnitude is even smaller, and you see it reflected in terms of the coloration that you see for that corresponding compound. So now for us to be able to have some appreciation of what type of expectations you can have for these transitions, well, there are specific selection rules. And so these are the electronic transition selection rules. So there are two that we're going to focus on. The first one is the spin rule. So according to this rule, transitions must not involve a change of spin. Okay, so we're focusing on a transition of electron from lower energy d orbital to higher energy d orbital. Well, in order for it to be spin allowed, you cannot have a change in your spin. What that means is that the total spin of the system must remain the same, even though there's a movement of an electron from a lower energy to a higher energy. Okay. Then there's another rule, which is called the Laporte rule. Okay, so according to this rule, transitions must have a change of parity. And so this terminology parity has to do with the symmetry. So what that means is that if you're going to have a transition between orbitals, they need to be such that the symmetry of those that corresponds to the orbitals must change. So that means that you must go from something that is Gerade in nature to something that's ungerade, or vice versa, ungerade in nature to Gerade. But what's not allowed for the Laporte rule, you cannot have Gerade to Gerade or ungerade to Gerade, ungerade to ungerade. So what does that mean with regards to DD electronic transitions? Well, that means that all DD electronic transitions are in fact Laporte forbidden. Okay, so you may wonder, if it's Laporte's forbidden, why are we even talking about this? Because in reality, these type of transitions do occur, but they violate these rules. And so what happens is that we see this reflected in terms of the intensity of these transitions. So one thing that I want you to understand from this lecture is that based on how intense a transition is how allowed, and I'm putting this in quotation marks because this is a relative concept, is the intensity will be a marker of how allowed a particular transition is. So we know all DD electronic transitions violate the Laporte rule, and yet we actually do see these transitions. So what we're going to talk about are specific cases in which we observe violation of both the spin rule and the Laporte rule, and how we can gauge this level of allowedness. All right, so let's look at the first example. So the first example is of a metal ion in a coordination complex. So this is an octahedral field. And this metal ion violates the spin rule. It also, because we're talking about a DD electronic transition, also violates the Laporte rule. All right, so I don't actually have that on the slide, but that's understood. So we have in this compound manganese coordinated to 6 aqua ligands. It turns out that this is a high spin D5 metal ion. All right, so high spin. So what that means is that this is going to be a weak field, right? So there's a very weak magnitude for delta octahedral. And so high spin in this case means, because that term is relative, that we have 5 unpaired electrons. Okay, so all 5 of these unpaired electrons, they are spin up, right? So each individual one will have an ms of plus 1/2. And so in order for us to determine the overall spin of the system, in this case, it will be the summation of all the spin values. Well, here we have an overall spin of 2.5. Okay, so let's imagine that we have a transition of one of the electrons that are in the T2G orbital going into the EG. So we're going to have this excitation where we're going to move one of the electrons. So let's imagine moving this electron into the higher energy EG. And in order to put it into the higher energy EG, what that's going to require is to have a flip of the spin in order for you to have 2 electrons into one orbital, as they cannot, in terms of energy, energetically, you cannot have them paired spin up. Okay, so we end up with the system that we have to the right. So now we're focusing on the right, and what do we see? Well, because of that excitation of that one single electron, we have a situation where we have 2 electrons that are paired up, and they're paired up in opposite directions. And so when we account for how many unpaired electrons, well, here we have 3 unpaired electrons. And so as a consequence of having those 3 unpaired electrons, when we calculate the overall spin of the system, now this spin is S equals to 1.5. So we now have a delta S that is 1. And according to the spin rule, you cannot have a change in spin. So that is why this particular transition is spin forbidden. But we can actually see this transition, but we see it with very low intensity. So what I want for us to think about is what parameter, when you were first introduced to electronic spectroscopy, gives us an indicator of intensity. And it turns out when you revisit the Beer's law, according to Beer's law, you have absorbance, and that equals to the product of the extinction coefficient times the path length times the concentration. All right, so it turns out that the extinction coefficient, well, that particular parameter is the measure of intensity. So this is here path length. This one is your concentration. So we're going to actually focus on the extinction coefficient as a measure of how allowed a particular transition is. And so as you can see here in what I wrote in the slide, well, this particular transition where you have spin forbidden, Laporte forbidden, well, they are extremely weak. And because they are extremely weak, your extinction coefficient will be extremely low. And so here is a estimate of how low. Your extinction coefficient will be less than 1 per molar per centimeter. You may also know the term extinction coefficient as molar absorptivity. That's another way that you can say the same concept. So this is something that you have to internalize. This is an actual constant for a given compound in solution, and we're using this as our gauge of how allowed. So this is going to be an example of a spin forbidden, Laporte forbidden transition. All right, so let's look at an example of something that is actually spin allowed, okay? So for it to be spin allowed, we're looking at a system that has a change of 0, so no change, of your spin after an excitation occurs. So here we're looking at, sorry about that. There we go. Waiting for this to catch up. All right, so here we have an example of a compound where you have cobalt, and it's cobalt 3 plus, coordinated by 6 aqua ligands. So that's cobalt 3 plus, which is high spin D6. All right, so high spin D6, what we're going to have then, a low delta. So that's going to be a weak field. And so you're going to have your 6 electrons in your octahedral field distributed in this manner. All right, so how many unpaired electrons do we have here? Well, here we have 4 unpaired. And because we have 4 unpaired, our spin is a total of 2. So now let's imagine an excitation of an electron from this particular system. Well, the excitation is going to occur with the orbital that has the paired up electrons. You're going to have an excitation from here to the higher energy EG, and so you're going to end up with the system to the right. So the system to the right, now you have that pairing now in the EG orbitals, and you still retain a total of 4 unpaired electrons. So because we have 4 unpaired electrons, our spin is going to be a value of 2. So we have a system here that after the electronic transition, you still retain the same spin. So there is no change of spin. Delta S is equal to 0. All right, so what does that mean? Well, that means that this particular system is spin allowed. It's still Laporte forbidden, okay? So I'm going to keep reiterating that. I'm going to be annoying about it. It's Laporte forbidden, but spin allowed. And because it's spin allowed, you're going to have a bigger extinction coefficient than you do for a spin unallowed or a spin forbidden. But even though you have this value between 10 and 200 per molar per centimeter, it is still considered extremely weak. All right. So let's look at another example of something spin allowed, and we're going to see something, an important difference. So remember that when we talk about these types of complexes, you can have different geometries. So this idea of delta octahedral is because we're focusing on octahedral, but this idea of delta can correspond to any geometry. So here I'm giving you an example of tetrahedral complexes, and an important difference that can exist for these type of complexes relative to octahedral. So here we're focusing on an example of spin allowed for a tetrahedral complex. So this complex that we're focusing on is nickel coordinated by 4 chloroligands. And this nickel is nickel 2 plus, which in this particular compound would be high spin D8. Okay, so high spin D8, well, by its nature, this delta tetrahedral, okay, is going to be weak field, right? We've already discussed this, how delta tetrahedral is always smaller than delta octahedral. So typical delta, excuse me, typical tetrahedral field will be high spin. So if you have D8, this would be the distribution of the electrons. And so what do we have here is a spin of 1 because we have 2 unpaired electrons. If we excite one of those electrons from the lower energy orbitals to the higher energy orbitals, well, we see to the right that you still retain 2 unpaired electrons and you still have an S equals to 1. And so delta S is 0. Okay, so this is spin allowed. But something I want to point your attention to, so let me actually clean this up a little bit, is here. So it turns out that when you're talking about something tetrahedral, and you should be very familiar with this by now, tetrahedral complexes are going to be non-central symmetric in terms of the general compound. So we're not, again, we're talking about crystal field theory, so we ignore the identity of the ligands. So the general tetrahedral compound will be non-central symmetric. Because it's non-central symmetric, when you look up the character table and you look up the labeling of the energy of these orbitals, well, you see that this is E and this is T2, right? Because non-central symmetric, we don't take in consideration Gerade or ungerade. Whereas when you talked about octahedral, right? And we looked at the character, the irreducible representation that defines these orbitals. Well, here, because octahedral is centrosymmetric, that is why you have the terms Gerade in as part of the descriptor of those particular irreducible representations. Well, because of the loss of that centrosymmetric nature, it turns out that for tetrahedral compounds, the extinction coefficient is actually higher than it is for a spin-allowed octahedral. And so this is something that is an important part that has to do with the symmetry of the tetrahedral compound that makes these type of transitions even more allowed, right? So that's why you have a higher extinction coefficient, which is now 100 to 1,000, whereas in the octahedral example, it was 10 to 200. So you see how the ranges differ. Okay, so that's an important distinction to make. All right, so any question about this? You can feel free to get on your mic or you can write the question in the chat and I can respond to it. All right, so I will move ahead, but again, feel free to stop me if you have questions. All right, so the other type of transition that we're going to talk about is those transitions that are called charge transfer. So as the name implies, you're transferring charge and you're going from one entity to another. So what entity are we talking about? Well, since we're talking about metal ligand interactions, well, that's what we're referring to. The movement of charge between the metal to the ligand or even vice versa, the ligand to the metal. So it turns out that these type of transitions are in fact both spin and Laporte allowed. And because they satisfy both of these requirements, right, these electronic transition spin rules, then what you will see is that the extinction coefficient for these type of transitions are going to be high. You're going to see extinction coefficients that will be greater than 1,000 per molar per centimeter. And so that distinguishes these two types of transitions. Charge transfers will have a higher allowedness, a higher extinction coefficient than the DD electronic transitions. But another really important difference is that these type of transitions are visible, are observed. Let me just make it more clear. Are observed in the UV range of light, whereas the DD electronic transitions were observed in the visible range of light. So these you will not have a coloration, something that you can actually see with your eyes. So let's define what these type of transitions are. And so here, even though we were using crystal field theory to talk about the DD electronic transitions, we're going to also incorporate molecular orbital theory to an extent in our discussion here. So one of the two types of charge transfers is called the ligand to metal charge transfer, and it's abbreviated LMCT. All right, so what does that mean? Well, that literally means movement of electrons from the ligand to the metal. okay? And so if we're using terminology from molecular orbital theory, well, what that means is that you're moving electrons from an orbital with primarily ligand character to an orbital with primarily metal character. All right, so where do we observe this? Well, actually, even though I have my notes here saying pi donor ligands, right, you can actually observe ligand metal transfers for all types of metal complexes. And that's because you're going to have the sigma interactions that are present in all metal ligand complexes. But where it can be particularly pronounced would be in pi metal complexes with pi donor ligands. So what I want to note is that this is not specific just to complexes with pi donor ligands. So just to note that. All right, so that's an important distinction. And then the emphasis being that pi donor ligands are where it can be particularly pronounced. So here we go to our diagram where we were talking about sigma only cases, and then when we're talking about cases where we have weak field ligands to the right, when we include the pi interactions from pi donor ligands. So for you to observe a ligand metal charge transfer, they're going to come from ligand, primarily ligand character orbitals being excited into metal orbitals. So for instance, in the the sigma only model, well, they will be coming from these, which are ligand, going into these, which are metal. All right, so that's what it means to be ligand to metal. And so those type of interactions can still be possible when you go into the context of a pi donor ligand system. But here, what you can also see is this is where I was mentioning to you more pronounced, more likely to be observed, is that you also have the ligand metal charge transfer bands that can come from the ligand pi orbitals being excited into the this is ligand into the metal orbitals. Okay, so again, ligand character excited into metal character. So this is to give you a refresher what we just talked about last week about including in addition to sigma interactions, pi interactions. So here's where we will particularly see ligand and metal charge transfers. All right. But what's the other type of charge transfer? Well, the other type of charge transfer is the metal to ligand charge transfer. So as the name implies, we're moving electron from the metal into the ligand. And so here is where we have to focus on what type of compounds allow that, because it's not actually observed in every single compound. So in terms of molecular orbital theory, it's a transfer an electron from an orbital with primarily metal character to an orbital that's primarily ligand character. And so you're going to observe this with pi acceptor ligands. All right, so that is actually a requirement for this to be observed. You have to have these pi acceptor ligands, those that can accept electrons from the metal. All right, so again, here is the molecular diagram. We're focusing on the cases where we have a strong field ligand. Those are going to be the ligands that have the pi acceptor capability. So this is a sigma model, as we established before. There's a ligand character, metal character, ligand metal transfer. But here, when we're looking at the pi part, this is the part that allows for ligand metal charge transfer bands. But then our focus being metal ligand, okay, this is the part where you can see metal to ligand charge transfer, because here, this is the orbital that was metal in character, and this is the orbital up here would be ligand in character. And so that's where you're going to have a metal to ligand charge transfer, because up here, this orbital that was generated and has ligand character, well, it's not filled, there are no electrons there, and it's capable of accepting electron density from the metal when you excite from the metal character orbitals. Okay, so that's where you will actually see it. All right, so how does this play out in reality? So let's say that you want to characterize this, you want to go into a lab and you're studying metal compound. Well, how do we actually observe this? So when you prepare solutions, you have to keep in mind the type of transition that you want to observe. because in order to see them, you need a specific type of concentration. Remember the relationship in terms of Beer's law. You have absorbance equals to the product of the extinction coefficient times the path length times the concentration. And if you're using a standard UV-Vis instrument, the path length would typically be 1 centimeter. Right? That's the cuvette that you use. And so when you want to then visualize in your, your spectrum, so you're going to have your absorbance and your wavelength. And I think you're typically taught that you should see things up to an absorbance of 1. Okay, so thinking about that, how are you going to see something in a absorbance in that range? So if you focusing on the observation of DD electronic transitions, because those tend to be of a low extinction coefficient, what you need to do is work with concentrated solutions, because then you'll be able to see them in your UV-Vis spectrometer. So DD electronic transitions will be seen in the visible range. This is a reminder of what we already talked about. They have generally low extinction coefficients. So for you to see them, the suggestion is to make millimolar concentration of your solution to be able to see them. Now, in contrast, if you want to look at charge transfer electronic transitions, well, these have higher extinction coefficients. So because you have higher, what you need to work with, you need to work with dilute solutions as opposed to concentrated solutions if you want to see DD electronic transition. And so you will see these in the UV range. And the suggestion is to make solutions that are micromolar concentrations. Now, if you want to try to see both of them in the same solution, the suggestion is to do something that's intermediate, that's going to be high micromolar, sub-millimolar, and you might be able to see both type of transition if that's what you're looking for. Okay. Any questions that you have about this? Any doubts before we move on? Okay, so we're all good with this? Perfect. Let's go ahead and we'll move on. All right, so that was meant for an introduction to this idea of spectroscopy, but it can be a little bit more complex. But for us to be able to appreciate the complexity, we need to revisit this idea of electronic systems, the situation, how we represent them. So what we're going to talk about today is we're going to define how do we represent multi-electron systems. So you might be wondering, well, didn't we do that at the very beginning of the course? And in fact, the very few first lectures were doing that. But there's one part of this that we didn't actually achieve in when we were representing multi-electron systems, and that's what we're going to do right now. All right, so for us to appreciate these DD electronic transitions in a more realistic manner, we need to understand multi-electron systems. And here, for us to define the electronic situation, we go back to the basics, quantum numbers. So there was one situation that we had previously ignored, and we're going to look at that example here. So we defined the quantum numbers for an electron in the valence shell of the p orbital of an oxygen, as this is our example. So we did a lot of this at the very beginning where I asked you your electron configuration. I actually still do that even today. What is your electron configuration? Because that's always going to be very important when you're defining the interaction between, atoms within a molecule. All right, so here we're looking at oxygen and we're focusing on its valence shell, and we're looking at this part, which is the n equals to 2. And of that, so if you think about this in terms of the energy, right, you have 1s, you have the 2s, and then you have the 2p orbitals. All right, so we have that. Okay, so that's a situation. The highest energy of that obviously is going to be this one, and that's actually what we're going to focus on right now. All right, so how do we actually define the electrons in the 2p? So if you think about the quantum numbers that correspond to the 2p orbitals, what you're going to have are values of m sub l of +1, 0, and -1, right? And we can put 3 out of those 4 electrons into those orbitals, right? So that's just the p orbital. So Don't get, confused that that's something different. That's just the two p orbitals and the three of them. But the thing is, how do we define a fourth electron going into these orbitals? Because that electron can go here, or it can go here, or it can go here. But how do we actually define it? How do we represent that? And so what we're going to do is to define additional quantum numbers to be able to do so, or revisit certain quantum numbers to help us do this. All right, so we're going to take into consideration the interaction of electrons by coupling the magnetic fields generated by their spin or their orbital motion. All right, so that's what we're going to factor in here. All right, so I'm introducing this quantum number L. Quantum number L is the total orbital angular momentum quantum number. And it actually is very related to the quantum number L, okay, lowercase l. Remember, lowercase l defines the types of orbitals in terms of the electronic situation, the shape of them. It turns out that capital L parallels lowercase l. So this total orbital angular momentum parallels the identity of L. And then you also have this parameter ML with capital L, which is the resultant orbital magnetic quantum number. And so that particular parameter, M sub L, is actually, in terms of how you determine it, is the summation of all the values of M sub L. And it turns out that there are different possible values of M sub L, and they are defined by the actual value of L itself, where the values can range from plus L all the way down to negative L. Okay, and so these are going to be in these values, and that defines all the possible values of M sub L can be. Where, if you note that at the highest end, the maximum value of M sub L is actually equal to the value of L. And that's going to be important later on when we start to try, when I look at a system and when we have to determine what is the value of L of that particular system. All right, but keep that in mind. So we're introducing this quantum number L. So as I mentioned to you, L parallels little l. All right. And so what does L represent in actuality? Well, it represents an atomic state, whereas little l represents an atomic orbital. So what's the distinction? Well, the orbital is the orbital itself, whereas the state has to do with the distribution of electrons within those orbitals. Okay, so L0 is the state capital S, 1 is the state capital P, 2 is the state capital D, 3 is the state capital F. These names S, P, D, and F refer to sharp, principal, diffuse, fundamental, if you wanted to just know where that came from. Whereas when you look at lowercase l, 0 is the s orbital, 1 refers to the p orbital, 2 the d orbital, 3 the f orbital. Right, so that's just a refresher of what a little l represents in terms of the orbitals. All right, so we're gonna revisit the quantum number s, which is the spin state. So this is the total spin quantum number, and is the sum of the electron spin. So the m sub s is the resultant spin angular momentum magnetic quantum number, and that m sub s equals to the summation of the m sub s, the small m sub s values, the direction of your spin. Whereas very similar to what we defined from m sub L, m sub s ranges possible values of plus s all the way down to minus s, where, if you note, the highest value is actually, the highest maximum value of m sub s is actually equal to s. And that actually becomes important later on when we define a specific system. All right, so quantum number s and quantum number L are what we're going to use to help us to define particular electronic situation. An additional thing is this parameter multiplicity. And I've referred to this name previously, but we're going to look at it more closely because multiplicity is another way that we basically state what the spin of a system is. So the multiplicity is equal to 2s plus 1. All right, so we're going to look at, well, how we correlate certain multiplicity to certain spins. Well, if you have a spin of 0, right, and you plug in this value into the equation, 2s plus 1, well, that's going to give you a value of 1. All right, so that gives you a multiplicity of 1. So what does that really mean if you have a spin of 0? Well, that means you have a system that either has no electrons or all of the electrons are paired. Okay, so that's what that means. When you have a multiplicity of 1, your particular system is a singlet state. Okay, that's what a multiplicity of 1 means. All right, let's look at an example of spin of 1/2. Well, what would be the multiplicity? Well, you plug in 1/2 into this equation for multiplicity, and that gives you a value of multiplicity equals to 2. Okay, so that means that you have one electron, and that electron can either be spin up or it can be spin down. It doesn't matter because spin is going to be an absolute number. All right, so you have a spin of 1/2. So what does that mean that your multiplicity is 2? Well, that means that your state is a doublet state. Okay, that's what a multiplicity of 2 means. All right, well, what about a spin of 1? Well, a spin of 1 means that you have two unpaired electrons. They can be spin up in two different orbitals, or they can be spin down in two different orbitals. You plug the spin into the multiplicity equation, and you get a multiplicity that's going to be 3, and that is a triplet state. Okay, so basically, multiplicity is a way of simplifying what the spin value is to define the state, whether it's singlet, doublet, triplet. Okay, so that's basically how we use the multiplicity. It's a representation of the spin, but it also simplifies how we define the state into these integer values, singlet, doublet, triplet. Okay, so now for us to represent the distribution of electrons and to better define the electronic situation, we're going to invoke Hund's rules. And so this is the first rule. According to this rule, it's the rule of maximum multiplicity. What does maximum multiplicity mean? You're maximizing how many unpaired electrons you have. And so this states that the ground state of an atom will be one that having the greatest multiplicity, meaning you're maximizing the number of unpaired electrons. That's according to Hund's first rule. All right, let's look at that in practice. So what we're going to do here is to represent how we distribute electrons in a particular set of orbitals. And this is referred to as the microstates. That's the distribution of electrons in a given set of orbitals. And so how we distribute them into these microstates, we are going to represent them by terms that are called Russell-Saunders term symbols. So how we represent those particular states. And this helps us to define the electronic situation in a more precise manner. Okay, so let's look at an example. So this is something that's more tangible that you can actually understand. All right, so we're going to focus on carbon. And carbon, in terms of its electron configuration, you may not have your periodic tables right in front of you, so I'm cheating right here. The electron configuration is 1s2, 2s2, 2p2. All right, so immediately we're going to knock out the core orbital, because this is focused on the valence orbitals. And in fact, what we're going to focus on in terms of electronic situation are the electrons in the open shell orbital. So here we're actually also going to ignore the 2s. So we're only going to focus on the 2p. So we're only considering the electrons there. All right. So we go back to 2p orbitals, and we have this particular state where we have m sub l, lowercase l, +1, 0, and -1. So we have to ask ourselves, how can we put those two electrons into these orbitals? Okay. And remember that in a given element, all of these three are degenerate orbitals. Okay, they are equal in energy. So those two electrons can go into any one of those because they are equal in energy. All right, so let's focus then just on the P2, right? And the different arrangement of these. And we're going to only focus on 3 possibilities. Okay, and I'm telling you, we're defining only those 3 possibilities for now. So one possibility is that we have one electron in the ML +1 and one electron in ML 0. Okay, so that means we have 2 electrons. They are unpaired and they both are spin up. So in terms of then determining the spin of that system, well, that's going to be a spin of 1 because we have 2 unpaired electrons. And then the multiplicity here, multiplicity will be a value of 3 because we have an S equals to 1. All right, well, what about another possibility? Another possibility is having two electrons and they're paired, and those two, I just put them here. I could have put them in the 0, I could have put them in the -1. I chose to put them in the +1. So we have these two electrons, they're paired up, so one's flipped up, one is flipped down. Overall, you have a spin of 0, and overall, your multiplicity is 1. So this is a triplet state, and this is your singlet state. Okay, so what's the last possibility that we're going to focus on? Well, the last possibility is this one. Again, I chose this, where we have one electron in +1, one electron in 0, but one of the electrons is spin up, one electron is spin down, meaning that your overall system will be a spin of 0. So overall, this will be a multiplicity of 1. This is also a singlet state. Okay, so these were 3 possibilities. There are more, but we're only focused on these 3. And you see how they're different in terms of their states. One of the triplet ones, the other 2 are singlets. And they're even though they're singlets, they're not the same ones. Okay, so let's clean this up for you to see this. Well, let's look at them individually. The top one, it turns out, is a representation of your maximum multiplicity. And in fact, of all the different arrangements, of all the different microstates that can be formed, it is the most stable. Okay, and so what does it mean the most stable? Well, it follows Hund's rule. The second one, which is singlet state 1, well, there's a penalty here, and there's a Coulombic repulsion because these are paired up. They're going to have these 2 negative charges resulting in electrostatic repulsion, which causes for a penalty. So this state, by its nature, will be less stable than obviously the triplet state that we have here. And then this other singlet state, well, here, even though we don't have a pairing up, we have a penalty due to an exchange energy. All right, what does that mean? Well, these two, remember, these two can be in any one of those orbitals, but in order for you to retain spin up and spin down, if you try to move one from the other, right, and retain the same system, you have to go through a flipping of the spin, possibly. So as you flip the spin, that requires an energy. And so that energy makes it so that these electrons cannot freely flow from one orbit to another because you have to go through this exchange energy penalty. And so that's why these two are higher energy states or higher energy microstates. And then this is your representation of the maximum multiplicity, but also very importantly, the most stable microstate. All right, so how do we represent this? How do we make this very simple for us to define what these states are? So we're going to talk about this idea of the Russell-Saunders term symbols. And I'm going to start off first by defining the method for representing the most stable microstate. So this is going to be the approach that you're going to do, in the next set of examples that when we discuss this concept for defining the most stable microstate. Okay, so what you need to do is, given the particular system, so in this case we have a P2, we are going to put those 2 electrons so that it follows Hund's rule. And so it turns out that by putting those 2 electrons in the highest values of M sub L, you're going to be able to define always the most stable microstate. Because remember, Hund's rule is that you want to maximize the number of unpaired electrons. So we're going to keep them unpaired. All right, so here, then, the ground state will always be identified by the occupancy of electrons in the M sub L of highest values in a manner which respects Hund's rule. So we put them in the highest M sub L and we kept them unpaired. All right, so now I'm going to show you then how we represent this in terms of a term symbol. So the first thing we need to do is we have to calculate what the value of L is. So here we have exactly 1 electron in the M sub L plus 1. And we're going to sum that with the 1 electron in the M sub L of 0. Okay, because if you recall, your actual maximum L is the summation of these M sub L's, the absolute value. So this is going to be 1 plus 0. So the absolute value that gives us a sum that's going to be equal to 1. Okay, so your L value for this system is a value of 1. When we look at the table, 1 is an atomic state of P. So this is a P state. So that's part of how we define the term symbol. So we need the L and the corresponding atomic state, but we also need the multiplicity. So we need the L and the multiplicity. But we already have the multiplicity because we calculated that up here. The multiplicity is a value of 3, is a triplet state. So the Russell-Saunders term symbol to define this particular system would be a value that's going to be 3p, where we put it and we draw it like this, where we have the p value and then we have the multiplicity as a superscript to the left of the atomic state. And that is our term symbol for the most stable microstate. All right, so that's the term symbol. But now what I'm going to show you is how we can define the term symbol for all the microstates, not just the most stable. But if you on an exam asks you give me the Russell-Saunders term symbol for the most stable microstate, this is the approach you should take because it will save you a lot of time. Unless I ask you to show me all of your work. Okay, that'd be a different story. All right, so Hund's second rule, because it's actually very important when we're talking about all of the possible atomic states. So if you have two states, so we're talking about atomic states, have the same multiplicity, the one with the higher value of L will lie lower in energy. So this is going to be very important when we determine all of the atomic states and we rank them in terms of their energy. We're going to use Hund's second rule. So now I'm going to teach you the rigorous approach to determining all the possible microstates of an electronic situation. I'm going to use an example so that we can go through this exercise. So we're going to stick with the P2. I like to recycle things so that it's easier to follow. So we're going to focus on the P2 system to do this. And then we're going to find terminology. So how do we put these 2 electrons into these 3 p orbitals? How do we do that in terms of how many possible ways of doing that? So how many possible ways is how many microstates, the number of ways you can arrange the open shell valence electrons. So here we'll define terminology. So one of the terminology is X, which X equals to the number of electrons. And so the number of electrons in the P2 system, well, that would be 2, okay? We're going to define this for our purposes of terminology L, which is the quantum number for the orbital. So that's not a new thing, you know that. The quantum number for the P value, excuse me, the P orbital is 1. L equals to 1. Okay. Then another terminology is this expression here, N subscript L. N subscript L equals to 2 times, in parentheses, 2L plus 1. Okay, so what does this actually represent? Well, here we're trying to calculate the maximum number of electrons possible for the particular orbital set. Okay, so that's what this is expressing. The maximum number of electrons possible for the particular orbital set. Well, here, we're talking about the p system, right? The 3 p orbitals. So how many electrons can go into p orbitals? Well, we can have a maximum of 6 that can go into here, right? But we don't have actually 6 electrons. We only have 2 electrons. So we have to think about then the arrangement of those 2 electrons in a system that can accept 6. All right, so that's where that particular terminology is coming from. All right, so we're going to need to use X, L, and N sub L. We're going to use that. And so how do we use that? Well, we use this to define an equation to determine the number of microstates, where we have NL prime divided by X prime times, in parentheses, N sub L minus X prime. All right, so we already defined what those parameters are. So now we can go ahead and start filling in this information. All right, so we have a system that's P2, and so N sub L is actually 6 prime, because 6 is the maximum number of electrons that can go into the 3 p orbitals. So 6 prime, we do the math. So 6 prime is 6 times 5 times 4 times 3 times 2 times 1. Okay, I already have it on the slide, but I wanted to write it out just for telling you where this actually comes from. X prime, so X is the number of electrons in the system. We only have 2 electrons, right? It's a P2 system. So it's 2 prime. So then 2 prime is 2 times 1, okay? And then the other term, NL minus X. Well, basically that's defining how many spaces do we have available. Well, if we have space for 6 and we're only using up 2, well, we have 4 spaces available. So this will be 4 prime. For 4 prime is 4 times 3 times 2 times 1. Okay. And so what we're going to do is we're going to eliminate common terms. So we eliminate this term, and that's going to give us 30 divided by 2, and that gives us a total of 15. That means we have 15 total microstates possible. 15 different ways that we can arrange those 2 electrons in those 3 orbitals. All right, so we're going to actually go about and do the work. All right, so 15 possible arrangements. So what I do, and the way I teach you is I create a table. So I have a table here. And if you notice, this table has a total of 15 slots because we have to arrange these 2 electrons in 15 different ways. And so in this table, I'm defining the M sub L +1, 0, and -1. And from that information, we can actually determine M sub L, and we can determine the value of M sub S. All right, so we can do all this in one table for us to keep this in track of. So the very first thing that I do when I think about like how do we go about doing this is I focus first on arrangements where we have things paired up. And then I focus on arrangements where we have things that are not paired up. All right, so we have here we can start off with having those 2 electrons, both of them in the +1, both of them being paired up in the +1. Okay, so that's one possibility. Then we have this other possibility here where they're all paired up, but in M sub L 0. And the third possibility is both paired up in the M sub L -1. Okay. We've exhausted all possible ways that you can have 2 electrons paired up in the system where we have 3 p orbitals. Okay, so now we have to move on to having a system where the electrons are not paired up. And so I do this in a very systematic way. So I first focus on the highest M sub L, just by practice. So I'm going to focus on having 1 electron in the M sub L1, and I'm going to have it paired up. So I'm going to focus on it when it's paired up, and then put the other electron in the other 2. So I can put the other electron into the 0. So I'm going to do it like this. Okay. I can also have this one paired up, right, with the 1 and the 0 paired down. Okay. And that's basically it as far as having the +1 paired up. Now, keeping the +1 paired up, the other electron has to go into the -1. So I can have this like this. And then the other possibility is the +1 paired up, and then the -1 being paired down. Okay. And so then I've used up that arrangement where we have +1 paired up. But now what I'm going to consider is, well, what about +1 paired down? What do I have then? Well, I'm going to do this one paired down, and then in the 0 paired up. The next one, this one paired down, and the 0 paired down as well. And that's it for those 2. Well, I can still consider paired down for +1, but put the other electron in the -1, so here, okay? And then I can put the +1 paired down, and then the -1 paired down as well. Okay, so I can do that. So now I've exhausted all the ways that I can put electrons in the +1 with the other electron in the other 2 orbitals. So now what's left? Well, now what's left is putting the 2 electrons in the 0 with the -1. That's what's left. Okay, so let's do that. So now we're going to move down to the 0. Well, let's do the same approach. That's going to be paired up, and then the other electron in the -1 paired up. And then in the 0 paired down, and the other one is going to be, oh, excuse me, that's not what I meant to do. Okay, let me correct myself. I meant to put this paired up and then the -1 paired down. Okay, and then we've exhausted those possibilities. So now let's go to 0 being paired down, -1 paired up, and then 0 paired down, and the -1 paired down. Okay, And that's it. We have put those electrons in these 3p orbitals in 15 different ways. And that's the only possible ways that you can do it. All right, but what else can we do with this information? Well, as I already mentioned to you, we can actually calculate the m sub L and the m sub S, okay? Well, let's start off with here. This one right here. We're going to start off with that one. Okay, so here we have two electrons. It doesn't matter that one is spin up and one is spin down. We have two electrons in the plus one. So what we can do here is that we're going to have for the m sub L is going to equal to 2 times plus 1. And we don't have any electrons in the 0, the -1. So we don't factor that in. Okay, so there's going to be nothing in the 0 and nothing in the -1. Okay, so then that is going to result in a total of a value that's going to be 2. Okay, so where do we put that value? We're going to put that value up here. That's going to be 2. But what about the m sub S? Well, in this case, because we have the electrons for the m sub S, we have the electrons spin up and spin down. Well, you're going to have a system here that's going to be then a value of 0. That would be a value of 0 right there. Okay. All right, so let's move on to the next one. So the next one, all right, the next one we have is going to be this one. All right, so let's figure out this one. So we have 0 in the plus 1. We have 2 in the 0, and we have 0 in the -1. So what do we end up with here? We end up with a result that's going to be 0 for your m sub L. But what about for your m sub S? Well, again, we have a situation where we have spin up and spin down, so that's also going to be 0 here. Okay. All right, so let's do the next one, this one right here. Okay, so that one, oh, I didn't mean to do that, but whatever. Go right here. All right. So we were here. All right. So here, so this was what 2, 0, 0, 0. All right. So we were here, and so what we're gonna have is the m sub L, m sub S. So here we have 0 in the plus 1, 0 in the 0, and then we have 2 in the -1. Okay, so what result do we get here? We're going to get a result that's going to be -2. Okay, and then here we also have a situation where we have a spin up and spin down. So this will also be a value of 0. Okay, all right, so that would be for the m sub L and the m sub S for those two, for those arrangements where we have them paired up. All right, so let's go to the next one. So the next one we had was this one and this one here. And I'm not going to do them all because otherwise you're going to get super bored. You're probably super bored already, but I just want to give you practice so you can see how it's done. So we're going to do this system right here. So here, you're going to calculate the m sub L. And here, since they're not paired up, right, you have where you have 1 that's in the plus 1. You have 1 that's in the 0. And you have 0 that's in the -1. Okay, so what's that going to be in total? That's going to be a value that's 1. So that will be a 1 right here. Okay, and then our m sub S. Well, we have a situation where you have plus 1 and 0. Both of them are spin up. So that's going to be a value that's going to be a total of 1. So we do this and put that at 1 right there. Okay, because they are spin up. All right. So you basically go through all of the different microstates and you define the m sub L and the m sub S using this summation of the m sub L's and the summation of the m sub S. All right. So that's how you go about doing for all 15 possible arrangements. All right. So let's skip ahead and we're going to show the responses so you can see the rest of the m sub L's and the rest of the m sub S. All right. So you have all that information What do we do with this? How do we determine the atomic signature? That's the big picture. We're trying to determine the representation of that P2 electronic situation in different atomic states. Okay, so we take this table that we have just created, and we're going to now process this data into another table. Okay, all right, so we're taking all the information and creating this table, which I have down here. All right, so what we have is arrangement of, in terms of your the top, the columns is +1 for m sub s, 0 and -1, and then the rows are for the m sub l's, +2, +1, 0, -1, -2. All right, where are we going to get information from? Where we get the information from up here? Okay, we're going to start putting the information and put it into our table. So let's look at, I always start off here with the m sub l, the row +2, the highest value. And I look at the different possible numbers that came from the microstates. So for +2, it turns out that we only have one arrangement, whereas m sub l2, and it's going to be with m sub s of 0. So I mark it in my table. And what I'm going to do is I'm going to mark it by putting an X right here. And that's the only representation we have for m sub l2, which is paired with m sub f of 0. Okay, so then I go now to the next one, which is m sub l of 1. All right, so I look for 1. Where's 1? So we have 1 here, 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 and that's it. Okay, so what do we have? Well, we have m sub l of 1 and m sub s of 1. Okay, and it turns out that there's only one of those. So I mark it here. Then I have of l, m sub l of 1 and m sub l of 0, and I actually have it twice. So I mark that here and here. And then I have an m sub l of 1 and an m sub s of -1. So I mark that here. And that's it. We're done with that. Then we go into m sub l of 0. And again, I look for all the zeros. Let's see if I can clean this up a little bit. I'm going to look at the zeros for m sub l. Okay, that's what we have. And so I focus on m sub l of 0. Do we have any m sub s of 1? Okay, and so here we in fact have here. And I believe that's it. Okay, so I'm going to mark that here. And then the question is m sub l of 0 and m sub s of 0. Will we have that here? And then will we have it here and here? So here, here, here. And then m sub s of 0 and m sub s of -1, we have that here, and we'll mark that here. Okay. All right. So before you get bored with me, we're going to flash forward to then, with all that information, what do we have? Well, we end up with this. And actually, it's symmetrical, and it's supposed to be. So we've grouped up our microstates into columns of m sub s and rows of m sub l. Right? How do we use this information? Well, the way we use this information is that we actually deconvolute it into atomic states. And it turns out that atomic states are formed from an array of microstates consisting of 2l plus 1 rows and 2s plus 1 columns. Okay, so we're going to put them into arrays. So how do we do that? Well, we do this by focusing on what's available here in this table. All right, so I always start off with then looking at, just like I did with the previous approach, but I started looking at the m sub l +2. And a reminder for you guys that when you look at the first row, there's only one entry, and then m sub s of 0. So focusing on those values, remember that your highest value of m sub l is equal to your value of l. The highest value of m sub s is equal to s. So if we only have the l equals to 2 and s equals to 0 for the m sub l and the m sub s, well, that turns out to be that they are our values of l, which would be 2, and our value of s, which would be 0, based on this relationship that I described before. So when we're putting this array of rows by columns, well, remember, 2L plus 1 rows, so we plug in for 2, and then 2S plus 1 columns, we plug in for S. When we do that, we're going to get an array that's going to be 5 by 1. That array is for one atomic state. So then I look in my table and I actually have to remove that information from the table. We need an array 5 by 1 that's defined by L and 2. So that means that we're going to start off here, and I'm going to mark that one. And it needs to be 5 of these microstates need to constitute this atomic state because it's an array of 5 by 1. So I'm going to take all 5 of these that are constitutes 5 by 1, 5 rows by 1 column. And I take that information and actually remove it from my table, and that defines one atomic state. And later I'll show you how we determine the term symbol for that one atomic state. So we do that, and we take it out of our table, and now we're left with this information. And so now we move down to here, to the next entry of our table. And we do the same thing, where again, we recall highest M sub L is the value of L, highest M sub S is S. Here, the highest M sub L is 1 because we're starting off here. And then the highest value of M sub S in this table will be, because as marked here, right, we have something here, we have something here, we have something here. Well, the highest M sub S is plus 1. So we have a system where it's L equals to 1 and S equals to 1. So our array is going to be then 2L plus 1, we plug in the L, we plug in the S, we're going to have an array here that's 3 by 3. Okay, the 3 by 3 defined by these parameters, L1 and S equals to 1. So with that in mind, then we go into our table and we're going to literally take out an array of the 3 by 3. So 3 by 3. Okay, and that's what we did. And I'm going to pull that out of the table. I'll literally pull that out of the table, and what are we left with? Well, now we're left with one single entry, one single microstate. And so here we move down to the M sub L of 0, where it turns out that you only have one entry, which is also in here. Okay, so again, we looking back at this, the highest value of M sub L equals to L, highest value of M sub S is S. We have a system where we have L equals to 0, your S is going to be 0. Our array will be constituted by the 2L plus 1 rows by 2S plus 1 columns. We plug in the L, we plug in the S. We have an array that's going to be 1 by 1. So there's 1 by 1. We mark it, and we take it out of our table. We did that, and now we're done. So the next thing we do is, and actually use these symbols here to mark our atomic states. So I didn't do that with my little pencil here, but in the slides you see I actually noted each state that I removed from the table by a particular symbol. So we have the circle, triangle, and the square. All right, so that circle was defined by this array, where we had the M sub L2, which gave us a value of 2, L equals to 2, and also the S equals to 2. So now we need to define that particular atomic state. So if you recall, we need to know the L value and we need to know the multiplicity. That's how we define the term symbol. All right, so here then, our L is going to be an L of 2, okay? So we have to remember, if we go L, and then the atomic state, we have 0, 1, 2, and then you're going to have S, P, and D. Okay. All right. So here then, if we have an L equals to 2, well, that gives us a state of D, which is right here. And then we have an S of 0 for the spin. You plug that into your multiplicity, you get a value that's going to be 1, which is a singlet state. And that's why we have this term symbol, 1D. Okay, then you move over to the state that was defined by the triangle, which was a state that had this representation where your L is 1 and your S is 1. Okay, with that information, you have your L equals to 1, you go over here, that's going to be a P state, so that's our P. With an S equals to a value of 1, your multiplicity will be 3, so that's a triplet state, and this will be your term symbol for that particular state. So here we have so far identified the 1D state and the 3P state. The last one, the square, which was to represent the last entry in the table, And that was defined by these parameters that gave us a value of L equals to 0 and S equals to 0. When you have an L equals to 0, that's an S, and S equals to 0, you plug it into your multiplicity equation, you're going to have a singlet state, and so you end up with this term symbol of 1s, okay? So we end up with 3 atomic states, a 1d, a 3p, and a 1s, okay? Now we need to arrange these in terms of energy, following Hund's rules. So there were 2 Hund's rules that we talked about. The first one talked about the maximizing multiplicity, okay? And the second one talked about if you have 2 states that have the same multiplicity, well, how do we rank them in terms of the energy? All right, so it talked about the value of L for helping us to rank these. All right, so here, of these 3 states that we have, the one that is the highest multiplicity to follow Hund's rule would be this one right here. That's going to be your 3p. And so when we rank these, that's actually going to be the one that's going to be the lowest in energy, as it's the most stable. It's going to be your ground state. But then we have to think about the other 2. How do we factor in those 2? So recall Hund's first and second rules, which again, as I noted to you guys, the ground state will be one having the greatest multiplicity. And if you have 2 states that have the same multiplicity, the one with the higher value of L will lie lower in energy. Okay, so we know that this one here is our ground state. And we know that because we know that we have the highest multiplicity. Highest multiplicity. Well, then how do we distinguish between the other 2? Well, we distinguish between the other 2 based on the value of L. So that means D, excuse me, we have L equal to 2 and L equal to 0. So the highest one will be this one right here. And so that's going to be the next highest in terms of energy. So when we rank these, we do it like this. In terms of energy, this is our ground. And then the other 2 are arranged in this fashion, with this one being intermediate because it has a higher value of L, and then the S is going to be, the 1s will be the highest, okay? So basically, this tells us how we can define the electronic situation when we incorporate this idea of a quantum number L, how we define these atomic states for a particular system, and then the arrangement based on Hund's rules. That's going to be what we need to keep in mind. All right, any questions about this, doubts that you might have? Any questions, anyone?
No,
All right, everyone. Well, have a great rest of your day. Take care.
profesor, para que sepa,
Ajá.
estaba buscando esta presentación y aparecía la de la nomenclatura, eh, como que se duplicaron.
Okay, I'll fix that if that happened.
Entonces también le quería preguntar, lo del seminario de mañana, podemos ir presencial, ¿verdad? O,
You can see, I just, the spacing, no sé por qué cambiaron el salón del anfiteatro, lo cambiaron al el anfiteatro de Julio García Díaz. So, es menos espacio ahí.
ok,
Okay,
gracias,
but yeah,
profe.
you can try. Yep. All right then. Take care.
Eh, yo tengo clase en el momento de ese seminario, un
Yeah,
laboratorio.
remember I sent you an email. Please read your email because it's going to be something that is will I will try to project it virtually. So if you have class, perfectly fine, not a big deal.
Ok.
All right, bye-bye.